Hello, I'm Gabriella Dravecz from the Wigner Research Center for Physics from Budapest, Hungary. I will speak about the preparation of rare earths doped lithium niobate nanocrystals by ball milling method. The goal of the project is to produce rare earths doped nanoscaled lithium niobate crystals where the rare earth dopant acts like single photon source. This means that it emits exactly one photon at a time. In this presentation, I will only speak about the thulium-doped lithium niobate. For achieving the single photon emission, the double doping method was chosen, where ytterbium ion as codopant can excite the thulium ion. The ytterbium ion is a good candidate for this because of the large absorption cross-section and long lifetime. For the excitation of the higher energy levels, 2 or 3 ytterbium ions are needed. In this picture, you can see the energy transfer diagram for the better understanding. In this slide, these are the methods I've used in this project. Milling, wet and dry, and heat treatment were used for the sample preparation, and dynamic light scattering, DLS, and scanning electron microscope, SEM, for the sample characterization. First of all, I will speak about the sample preparation. Here you can see the mill we used. It's a planetary micro mill, from the Fritsch laboratory. If it's open, we can see the crucible with the sample, the milling balls and the solvent, if there is, inside. And at the opposite place, there is a balance crucible with the same weight. In the first picture, you can see the communication panel with the parameters, namely the rotation speed, rotation time, number of the cycles, and the length of the pause between the cycles. You can easily change them by the buttons below. For obtaining the lithium niobate nanocrystal, we tried the wet milling first, which was recommended by the manufacturer of the mill. Here you can see the parameters of the milling process. For the first experiments, dopants were not added to the mixture, only lithium niobate. The solvent was distilled water. The rotation speed 1100 rotation per minute. One cycle lasted 1 minute. We applied 10 minutes pause between the cycles. The whole process with the balls by one side lasted 10 cycles. We started the milling with the balls by the diameter of 3 mm. After we continued by the balls with the diameter of 0.5 mm, and finally the smallest balls were 0.1 mm. At the end of this process, the size of the particles we reached was between 5 and 20 nanometers, which is very good for the application. But there was a problem. The first thing we saw was the black parts of the sealing ring in the crucible, you can see in the picture. It's not only because of the mechanical wearing, but because of the formation of lithium hydroxide, which is a strong base and dissolved the sealing ring, the zirconium dioxide crucible, and the balls as well. So it must be eliminated because of the pollution of the sample and because of the damage of the crucible and the balls. We tried to replace the water by different organic solvents such as 2N-butoxyethanol or ethylene glycol. The same milling parameters were applied, namely the rotation speed 1100 rotation per minute. One cycle lasted 1 minute. We applied 10 cycles and the balls with the diameter of 3 millimeters. The frictional force was too weak for milling the crystal pieces. You can see it in the picture. The white ones are the milling balls and the transparent phases are the crystal pieces. So it was a dead end. The next step was the dry milling. The starting materials were lithium niobate, ytterbium oxide and thulium oxide with the molar ratio of 80 niobium, 1 ytterbium and 1 thulium. The diameter of the milling balls was 3 mm. The smallest ones didn't give better size distribution because of the adhesion of the particles, so we didn't use them. The rotation speed was 1100 rotation per minute and the number of the cycles was 10. The size of the particle we reached with this method was 30-60 nanometer. After every cycle, the ground material was dispersed in 2 propanol for complete removal of all parts from the crucible and balls. After that, the sample was dried for the next dry milling round in order to prevent the particles from sticking together permanently. The particle size we achieved was higher than we achieved by wet milling, or larger than we produced by the wet milling, but the dissolution of zirconium dioxide crucible, the balls and the sealing ring could be avoided. Yes. Before the milling process, the starting materials were ground and then sintered at 800 degrees Celsius for 2 hours in order to reach a homogeneous distribution of the ytterbium and thulium dopant. It was repeated one more time between the 5th and 6th cycle of milling. After the milling process, grayish coloration of the dried sample can be observed, which is well known from the literature as a result of polaron formation and can be eliminated by a heat treatment during 2 hours at 800 degrees Celsius. Now I will speak about the sample characterization. Dynamic light scattering (DLS) method was used to control the particle size. The verification of the homogeneous distribution of the ytterbium and thulium dopant was carried out by a scanning electron microscope. I have already showed the joke before, but now I will show the results in details. For the wet milling, the DLS show the distribution of the resulted particle size, which is mainly 10 nanometer, and they are in the range of 5 to 20 nanometers. In the SEM picture, we can see the shape of the particles. The crystallographic structure with the straight borders can be observed. The measuring parameters can be seen below the picture. The concentration analysis of the elements were also carried out by scanning electron microscope. In this case, a thicker layer of the sample was used. In the spectrum, we can see the material of the carrier, the niobium from the sample, and the zirconium from the crucible and the balls. Their amounts were comparable to the concentration of niobium. This limits the application, although the particle size was appropriate. The size of the dry milled sample was mainly 30-40 nanometers, in the range of 20 to 80 nanometers. This SEM picture shows the crystallographic morphology, in this case too. This sample was diluted to an appropriate extent, so the particles didn't stick together. In this case, we used even thicker layer of the sample for characterization. Ytterbium-thulium dopants and lithium niobate are clearly seen. The line of the zirconium is weak. This so little zirconium content occurred by the mechanical reactions during the milling process. For the application, it won't disturb us. In this slide, there is a technical information about the size and shape characterization of the particles from the diluted suspension. We added 0.2 weight% polyethylene glycol and 15 volume% ethylene glycol to the sample to assist the adhesion of the glycol and to assist the adhesion of the sample to the surface. Without these glue materials, the sample was eliminated by the vacuum of the microscope. Generally, a dopant element or ion can bring into the sample several ways. In this work, we used two techniques. The first, when the ytterbium ion were originally built into the lithium niobate phase by crystal growth technique, and the other, when the ytterbium ion was added to the lithium niobate phase as an oxide, and then heat treated and milled, as I have already mentioned before. For checking the incorporation of the dopant, photoluminescence technique was used, where the emission of ytterbium in lithium niobate could be recorded. Because all expected peaks can be found in the spectra and their shift is the same in both cases, we can say that they are in the same position. So the ytterbium ion is built in the lithium niobate phase in the second case as well. So sample preparation from raw materials can be used also. The conclusions of this work are the following. Dry milling method was developed for producing ytterbium and thulium co-doped lithium niobate nanoparticles with the diameter in the range of 30 to 60 nanometers. Dilution of the sealing ring and the zirconium from the parts of the crucible could be eliminated. Scanning electron microscope characterization was optimized for determining the shape of the particles and the concentration of the elements in the samples. Amount and quality of glue materials was optimized and used successfully. Sample preparation from raw materials can be work because the incorporation of ytterbium ion was proved by recording the emission spectrum. Finally, I would like to thank the National Research Development and Innovation Fund of Hungary within the Quantum Technology National Excellence Program for supporting this research. And thank you for your attention.